In undergraduate maths, specifically linear algebra, one of the first things you will learn about is the idea of independence. In essence, we say that a set of vectors is independent if they all give us something new. If you can write one of the vectors in terms of the others, then they are not independent. If I gave you a single non-zero vector, then it is independent with itself. If I gave you two non-zero vectors, and they both point in different directions, then they're independent. If, however, the two vectors both convey the same direction, then they're dependent. Each of the vectors is a scalar multiple of the other one in this case. If I gave you three vectors, we could get a bit more complexity. You could have all three vectors independent, in which case they span 3 dimensions, or you could have 2 of them independent, and one which can be made from the other 2. In this case, these 3 vectors will span 2 dimensions. In general, if n vectors are independent, then they span n-dimensional space. With 4 vectors, we once again could have all of them independent, in which case they span 4 dimensions, and we could have 3 of them be independent, in which case they span 3. Now, however, we could also have 2 independent pairs, or even we could have just these 2 independent and have the other 2 depend on each other. To really describe how exactly all of the vectors are independent with each other, you need to be able to list which sets of them are independent. In a vector space, we know that all of the independent sets can be described as subsets of a basis, and this idea will generalize as you'll see. So now let's ask the general question. If I gave you n vectors, then how many ways are there that they could be independent, or not, up to isomorphism? By that I mean, you can't just relabel things to make something new. Have a think about that for a while, or maybe try and write it down for the first few, say 1, 2, 3, 4, 5. So, what other ways are there of thinking about independence besides in a vector space? In graph theory, we could, for instance, take on a slightly different definition for independence. Here, we can say that a set of edges is independent if they don't form a loop or a cycle on the graph. This is similar to the vector space case, but with some important differences. Now, for instance, it's perfectly possible for a single edge to be dependent on itself. Quite simply, it just has to make a loop, starting and finishing at the same node. So now if I asked you with one edge, how many ways can it be independent or dependent? Now, there are 2 possibilities rather than 1. We could have that edge dependent on itself, or it could be independent, spanning between 2 nodes. If I gave you 2 edges, how many ways can this happen now? As it turns out, there are 4 ways, as you can see here. And we can continue in the same way with any number of edges. Both of these, the linear algebra sense of independence and the graph theoretical independence, are cases of a generalization of the idea of independence which we can call a matroid. To make a matroid, we need a few things. Firstly, we need a set of things to work on. I could, for instance, give you these 3 vectors, or this graph and all of its edges. This set of things is called a ground set, and we label it generally with E. In addition, we need a collection of subsets of E, which represents the sets of things which are independent. For example, on these 3 vectors, every single one is independent with itself, and the following pairs are also independent. The set of all 3 vectors here is not independent, so the largest independent set in this matroid has 2 things in it. This is what we actually call the rank of the matroid. So, overall, this is what the set of independent subsets looks like. We'll label this I. So, given these 2 things, the ground set E and the set of independent sets I, they make a matroid if they do 3 things. Firstly, subsets of independent sets also have to be independent. This is relatively intuitive. If I gave you 3 independent vectors, for instance, they don't suddenly become dependent if I take one of them away. We can take any subset, and they still have to be independent. Next up, the empty set also has to be independent. This makes sense. How can a set of things be dependent if there isn't anything which can depend on anything else? Or from a more formal set theoretical point of view, the empty set is always a subset of any set, so if you want all subsets of independent sets to be independent, then so is the empty set. The last thing we need actually looks a little bit different from the first 2 and is a little bit harder. If you've done linear algebra, you'll know that if you're in a vector space with a basis of dimension 3, and I give you 2 independent vectors, then you can steal something from that basis to make a new set of 3 independent vectors. In essence, if you have an independent set and there is a bigger independent set that exists, then you can steal at least one of the things in the bigger set to make a new independent set. And that's it. If your E and your I do all 3 of these things, then you have a matroid. So let's go back to our earlier question and try to generalize it. How many ways are there for n things to be independent in any general matroid structure? If I gave you 0 things, how many ways can it be independent? Well, 1 way. And here it is. It's nothing. E equals I equals empty. If I instead give you 1 thing, then we now know that it can be independent with itself, as in the vector space sense, or it can be dependent on itself, like a loop on a node in a graph. So there are 2 ways. If we continue in this fashion, the numbers look like they're growing like 2 to the n for the first few. But then suddenly, quite weirdly, they get very, very big. Despite the fact that it looks like it starts out like 2 to the n, we know this number actually starts growing something more like 2 to the 2 to the n in the long run. So if I gave you 10 things, just 10, then how many ways can they be independent? The joke is, we don't actually know. But we know it's a lot more than 1 million, certainly. We know how many matroids there are of size 9 up to isomorphism, and it's already pretty big, but size 10, right now we just don't know. Fundamentally, I find this really strange, and for that reason really cool. For as few as 10 things, we just don't know how many ways they can be independent of each other. For something simple enough as the idea of independence, which we intuitively come across in our first year at university, we just don't know. And that's why, at least right now, despite not knowing it, this is my favourite number. And to be honest, I'm much more interested in the things that we don't know than the things that we do. My name is Keenan Down, and to be honest, I'm not sure if I'll post very often on this channel, but I might every now and again. I've been meaning to revive it in some sense, but subscribe if you're curious to see what I might create, because to be honest, I'm quite curious as well. And, of course, thank you for watching.